Greetings. My name is Aryan Garg, and I'm a student of Physics 2211. And today we'll be talking about Lab 1, which is constant velocity motion. The purpose of this lab is to basically observe a one dimensional constant velocity motion and then track and analyze this motion using Tracker. We'll be using Newton's second law to model this motion and then compare this data from Tracker versus a computational model written in GlowScript. The main result of this lab, before we dive into it, is that the computational model matches the tracker data pretty closely, that the position increases with time linearly, and that the net force acting on the object in our case is zero, which means there's constant velocity. The physics model we'll be using for this experiment involves a object moving with a constant velocity in direction x. Newton's second law states that the net force is equal to mass times acceleration. If this net force is zero, then the acceleration is zero. And if the acceleration is zero, then the velocity of the object is constant. The position equation we'll be using will be x at position t equals to initial x, which is the position, plus velocity times time. Moving on, the system and assumptions we'll be using in this lab is that the system is an object in motion, in our case a marker. The surroundings are a table surface and air, and that the object is assumed to be moving in one-dimensional motion with net force zero, negligible friction, and a constant velocity. The object is of a mass 0.005 kilograms with the initial position and velocity as written on the slide. The net force again is acting as zero, time step is 0.01 seconds, and simulation time is 1.15 seconds in our case. Experimental setup involves us keeping a marker on a table and recording it with a phone, which is stationary. It moves in a straight line. The calibration object for our experiment is a meter scale, which is highlighted in blue, and then the motion is analyzed using Tracker. Upon Tracker analysis of this marker as a point of mass, we see three graphs on our right, along with a chart talking about the time, the position, the velocity, and acceleration of the object from time 0 to times 1.133 along with the graphs. We'll dive more into it as we move on. The model output for our computational model is basically based off of three main equations. The first one being the momentum principle, the second one is the net force is zero, and the third one is that the new position is equal to O plus velocity times t. On our right, we see the initial conditions with the mass, the position, and the velocity, times and delta t, along with the two equations, which is velocity equals to initial velocity plus force divided by mass times delta t, as well as the equation for position, which is initial position plus velocity times delta t. This final velocity and position for each time frame is then printed out by our computational model that is written in GlowScript. The output for this model involves two graphs, which is the position time graph, which is a straight line with a constant slope, constant positive slope, and then a velocity time graph, which is just a straight line, meaning that the velocity remains constant throughout this time period. If we compare the data from the model and the tracker and superimpose them onto each other, we see this graph, which means that the data closely follows each other. The computational model, which is simulated from 0 to 1.15 seconds, as well as the tracker, which is 1.133 seconds, we see that the trend continues. Now, the tracker data has some noise, which means it doesn't model exactly. However, the slope, as well as other physical conditions, remain fairly similar. Now, why is that? Why do we see that there's an identical slope of position and time graph for both? Both the graphs have a linear relationship. There are small deviations, but this may just be due to measurement errors, inconsistencies, and some surrounding noise. The possible error sources for this similarity is that tracker involves manual marking. There may be calibration errors, or there may be small irregular friction forces acting on the object from the table due to the irregularity of the surface. Now, if we talk about what if the axes are flipped, in that case, velocity would be the same, but the magnitude also remaining the same, but the sign is reversed. Essentially, the slope would be negative and velocity would be negative, but the actual physical motion would be unaffected. Only the coordinates and quadrants would change. Another question that we're supposed to discuss is, what about zero net force? Zero net force here does not mean there's no forces acting on the object. Example, a forward push and friction may cancel each other out. However, all the forces acting on the object in all directions cancel each other out, leading to net effective force being zero. And these balanced forces lead to motion with a constant velocity, hence the steady slope. The conclusion is that the model was accurate and that when the net force is zero, it leads to a constant velocity due to zero acceleration, and it explains Newton's second law very well. Thank you and have a great day.